Up to now, our exploratory data analysis has used all the rows of the IRIS data frame. We've ignored the non-numerical species column entirely. Applying iris species.describe yields a curious result. The data frame returned has entries count, unique, top, and frequency. This tells us the column species contains a categorical variable or a factor, one that has a small number of distinct values. Count is the number of non-null entries, 150 here. Unique is the number of distinct values or categories, 3 here. Top is the most frequently occurring category, setosa, but it's a three-way tie in this case. Freq is the count of the most frequently occurring category, 50 here. Applying the unique method to the series iris species returns an array with 3 distinct values, setosa, versicolor, and virginica. Knowing that there are 3 different factors, it makes sense to carry out EDA separately on each factor. We can extract rows corresponding to each species by filtering. We first define a logical series indices in which the species is setosa. We slice on those indices and get a new data frame, setosa. We repeat this process to assign new data frames setosa, versicolor, and virginica. We can verify the new data frames all have unique distinct values in their respective species columns using the unique method. That being the case, the species column can be deleted from each. Actually, in this non-representative case, extracting factors is atypically easy. The original observations are sorted by species in the data frame iris, so we could split by species without filtering. We see this because the indexes for setosa, versicolor, and virginica are the integer ranges from 0 to 49, 50 to 99, and 100 to 149 respectively. It is possible to reassign the indexes, but we're not concerned about that here. In a later Pandas course, you can learn better tools for performing group by operations to extract factors. Let's repeat our EDA on individual species rather than the entire data set. Notice, we plot all histograms in one figure. We pass optional bins and range arguments to hist. We use transparency alpha equals 0.3 to help visibility. This is the histogram of the entire data set. Notice it's a bit messy with all of the histograms overlapping. We can make up similar plots for each species. Here are the related commands for the setosa data frame, for the versicolor data frame, and for the virginica data frame. Here are the setosa histograms, the versicolor histograms, and the virginica histograms. Where the collected data had significantly overlapping histograms with many confusing peaks, the separated factors reveal clearer trends for each measurement. The same point holds when computing statistics. Using the describe method with the entire iris data frame versus the individual factors leads to quantitative errors. We'll create data frames describe all, describe setosa, describe versicolor, and describe virginica containing the output of describe on each factor. We can compute the percentage error in all the statistics in each case. This is the absolute difference of the correct statistic computed in its own group from the statistic computed with the whole population divided by the correct statistic. Data frames can do element-wise arithmetic easily, so there is no need to write loops to compute errors for the mean, the standard deviation, the median, and so on. In looking at the percentage errors, the petal length and width show the greatest errors in using non-separated groups. This is suggested also by the histograms we saw earlier. These values give a sense of how misleading the statistics were when computed over the whole population rather than by factor. You'll see later how to group data frames. For now, try some exercises to get used to EDA with separate groups.